Okay, so let us start. Hi, can you hear me properly? Alright.
Yes, ma'am.
Okay. So some of the questions are repetition of what we already did. So again, I would request you to calculate and let me know what you are getting, and then I can solve it. So given this psi and dual vector phi, what will be the inner product? Can you let me know what you are getting for a and b, these two integers? Can you compute this inner product and let me know? You are solving, right?
Yes, ma'am.
Okay, then I'll wait.
Ma'am, 17 plus 16i.
Okay, so A is coming out to be 16 and B is coming out to be 17.
Yes, is that correct?
Yeah, that is correct. That is
Okay.
what you should get. So psi so when we take conjugate, we will get 1 minus I, 3, and 2 plus 3i, and phi ket will be 5i, 6. So the inner product of these two will be 3, 2 plus 3i, 5i, 6. So 5 times 1 minus I plus 3i plus 6 times 2 plus 3i. So as you said, it's 17 plus 16i. Okay. Okay, this question says consider two basis sets representing the same Hilbert space. The trace of an operator A in this basis is equal to the trace of that same operator in the other basis. Is this statement true or false? What do you think? if we take trace of this operator in this basis and then also take trace in this basis, will it be same or different, is the question. So any Hilbert space can be described by different basis sets. So here we are given any two basis sets, so the answer will turn out to be true. So let me explain it. Okay, now any vector in a given Hilbert space you can write as a linear superposition of the basis states. Suppose the vector space is n dimensional, so denote it as Vn, and so the basis vectors, the old basis vectors, can then be written in terms of the new basis vectors. Where j runs from 1 to n, because it is true for any state. So this basis sets, so we have these basis sets, let's think of these as old basis sets and these are the new basis sets that we have, n number of, because the vector Hilbert space that we are considering is of dimension n. So we know that any state can be written as a linear superposition of the basis states. So these basis states can be written in terms of linear position of these. That is what I meant here. Okay. Now any other state. So any other state can be written as, so what do we need to see? How this operator, when written in this basis, is related to the one when we write it in this basis. So that is what we need to see. So in order to see that, let's write any vector A alpha as summation over I.
Madam, what is S of di? S of di?
Yeah, no, it's Ji. I mean, yeah. So this is a set of numbers. Meaning, what I meant is that this is a vector. You can write this vector as a linear superposition of these vectors. So these are numbers, complex numbers. And any other basis vector, any other state. This is any state in the Hilbert space, not the basis vectors that we have here. Just give me one more. Sorry. Yeah, so any other state in this Hilbert space can be written as some number times those basis vectors. This can also be written as let's denote it E, so we can distinguish it because both are basis vectors, so we can express any state in terms of a linear combination of these or these. Now let me write it here. So here if we replace these basis vectors in terms of these, what do we get? So alpha vector I'm just replacing this EI kit here. So summation over j equal to 1 to n So what do we get? J is equal to 1 to n summation over I equal to 1 to n Okay, so what do we see if we compare equation 1 and 2? We see that AI, the components of this alpha vector, when it is expressed in F basis, it is related in terms of the components of E basis like this. So AIF, so I mean comparing equation 1 and 2. We can see that summation I equal to 1 to n. Okay, and so this is component by component. So I runs over 1 up to small n, and j is also 1 up to small n. So what I mean is that this can be written in terms of matrix, right? So A1F, A2F, ANF, this is like this matrix. So in matrix notation, we can write it as F basis, where S here is a matrix. Okay, this entire column vector I am calling this AF, and this is like A in E basis. Okay. Okay, having said that, now you also note that starting with these two, suppose we have this operator. Okay, this operator we are given. So when that operator acts on this alpha vector, so this alpha vector may not be an eigenvector of this A operator. So we should in principle get any arbitrary vector alpha prime. Okay. So, and we have said that alpha can be written as in this basis. So let's this is equal to now here we can insert an identity. So from completeness relation, because from completeness relation we know, using completeness relation,
Madam, can you explain what is completeness relation? Always we can find this one. What do you mean by completeness relation?
So in terms of these projectors, it would mean that, so this is the projector corresponding to all the basis vectors, and when you take summation for all these projectors, you should get an identity. This is, I mean, the nomenclature is called completeness relation, and it should be identity. So we can just insert that identity here, and what we get is a cap on alpha is equal to summation over now. So you can see that this is an element of that operator A written in E basis, so that we can write as A J I in E basis EJ. So this is equal to summation over J is equal to 1 to N, summation over I equal to 1 to N. Now we said that this alpha vector may not be eigenstate of A, so it shouldn't in principle give you some eigenvalue times that vector, but in general it should be some other vector alpha prime. So this is like alpha prime, some other vector is this. So that alpha prime can also be written as summation over J is equal to 1 to N A J in E basis. But so what do we get from here? We see that, so if I compare these two, comparing these two, we can see that left hand side and right hand side is equal to summation over I equal to 1 to N again. You can write it in matrix notation. So this is like A1 in E basis primed the operator expressed in E basis. Then the components of A vector when initially alpha vector, this alpha ket. So alpha ket we wrote as this quantity, this linear superposition of all the basis vectors where these were the components initially, and after we operate on that state, this A operator, the components are related to the initial components by this relation. That's what we wanted to show here. Okay, so again in matrix notation, so if I denote it as then A vector in E basis okay, so we got another relation, and here we had this relation we got by using the fact that there are two basis sets in the same Hilbert space. So that means the first basis set can be expressed in terms of the second basis state in this way. So when we use that property, exploit that property, we get that the components of any vector in the second basis can be written in terms of the components of the first vector in the first basis by this S matrix, where S matrix appears here. The components of S matrix appears here in the transformation of the basis vectors. So this is the okay. Now okay, so just like we got this using alpha in E basis, we can similarly do the same thing again. So when you write it in, so we also know that alpha can be written in terms of F basis, and if you do the similar analysis, you can show that A, so these are again the components, so the matrix, in matrix notation, this is what you will get. So we now have these three relations. Let me copy it again below. So okay, I used 1 and 2 before, so let me call it 3, 4 and 5. If S is non-singular, meaning determinant of S exists or S inverse exists, so then from this equation is equal to S inverse, okay. So these are all matrices, okay. I am using a different notation for A just to emphasize that these are all matrices. So this A in E basis is related like this, and then you can substitute it here in equation 3. So AE prime is, we want to see how these two are related. That is our goal here. S inverse, okay. Okay, now so this is so from 5 we can also have AF prime would be S, AE prime, call it 6. So substituting in equation 6, so it's S times this quantity. So what do we get? So this is nothing but, if you compare equation 4 and 8, you can see that AF, so the operator matrix form of the operator, given operator, when you write in F basis, that is related to the matrix form of the operator in E basis in this way. So AF is equal to, so it's called a similarity transformation. So these two are related by non-singular matrix like this. So the question is saying the trace the trace of that operator A, how is it related to the trace of that same operator in these two bases. So we now have this. So this is comparing comparing 4 and 8. Okay. This is also called similarity transformation. We know trace is cyclic, so trace of A in F basis will be equal to trace of S A in E basis S inverse. But since it is trace is cyclic, so S inverse will give you identity and you will be left with trace of the A in E basis. So yeah, I mean, yeah, so the thing is, trace of the operator will not depend on the basis that you are choosing. So yeah, so trace is nothing but sum over the eigenvalues, and it shouldn't depend on which basis you are choosing to represent the operator A.
Madam, the eigenvalue may be different. But the orientation means the eigenvalues are same, but they are oriented in different fashion. That means.
Yeah, so there are
That means
some
lambda 1, lambda 2, lambda 3, maybe lambda 3, lambda 2 and lambda 1 like that.
Exactly, because whenever you change basis, it's the matrix is related by similarity transformation and it will not change your eigenvalues because trace remains invariant. So the way you are saying that the order in which it appears in the matrix might differ, but ultimately the eigenvalues will not differ.
Madam, when we are doing an operation with any matrix operation, that means it is just giving a rotation of that vector like that.
So the linear transformation can be a rotation or a scaling. So this A, the operation that we are doing here, it's a linear transformation. This linear transformation can be general, but it should be such that A operating on this is like summation over I, then A operating on each of these vectors, basis vectors. So that is a linear transformation. And for any linear transformation, this property holds that for two different bases, the matrix will be related by a similarity transformation or S inverse, where S is a non-singular matrix. It can be unitary matrix. Okay.
Okay, madam.
Okay, this question is asking you to find out the normalization constant. Can you do that?
Is it 30, madam?
Yeah, A will turn out to be 30. Let me check still. Yeah, 30. Okay. This question, we are given operator U, which is exponential I alpha beta cap, and it says that this operator U is unitary. Then the condition on the parameter alpha and beta must be alpha real, beta Hermitian, alpha real, beta anti-Hermitian, alpha imaginary, beta Hermitian, or alpha any complex number and beta anti-Hermitian? What do you think the answer to be? First of all, what do I mean by unitary operator? You know that if U is if U is Hermitian, then we know that U dagger, that is transpose conjugate, should be equal to U. Anti-Hermitian would mean U dagger should be minus U, and likewise, what do you mean when you say that U, any operator, is unitary? So the definition of unitary operator is U dagger U equal to identity. So U here is exponential I alpha beta. So when we do U dagger, it will make it exponential minus I alpha star. Beta cap is operator, so beta dagger. So U cap dagger U cap will be exponential minus I alpha star beta dagger plus I alpha beta. Now for this to be identity, it should be equal to exponential of 0. So that implies same as alpha beta cap, or alpha has to be real and beta has to be Hermitian. Alpha star should be alpha and beta cap dagger should be beta cap. Is this clear?
Yes, madam.
Okay. We have to evaluate this commutator where X is position operator and P is momentum operator. Can you do this commutator? So we just need to know that XP commutator is IH cross. So what will be the value of this commutator?
Madam, D is D option.
D?
D.
B or D?
D.
This one, okay. Okay, let's see. I don't think it should be D. No, it's not D. D is not correct. So X Px square. So you can write it as plus and XP is IH cross. This is also IH cross, but P is itself minus IH cross ddx. So what do you get? 2h cross squared ddx. Okay, so B option is correct. Okay. If A and B both are Hermitian operators, then this AB plus BA and AB minus BA are also Hermitian. Is it true or false?
False.
Yeah. Which one is not Hermitian? So if you take dagger of this, you will end up with AB plus BA, because it's I think this kind of a problem we did last time also. And this will be anti-Hermitian. BA minus AB, so it's minus of AB minus BA, so it's anti-Hermitian and it is Hermitian. Okay. Which of the following statements are correct? The eigenvalues of a Hermitian operator are purely real. Eigenvectors corresponding to different eigenvalues of a Hermitian operator are orthogonal. The commutator of two Hermitian operators is Hermitian. If operators A and B are Hermitian, the product is Hermitian if and only if AB commutator is not equal to 0.
The A, B and C are correct.
C. Okay, D is not correct. You were saying A, B and C. Okay. Okay, let's see from C. The commutator of two Hermitian operators is Hermitian, you are saying. So if A and B are Hermitian, their commutator should also be Hermitian. Is that correct? Is it equal to?
If it is 0, then it is Hermitian.
No. I mean, this is different. So I mean, this option has no relation to this option. So here it's not. Here it is not saying anything whether the commutator is 0 or something. It's just saying the commutator of two Hermitian operators is Hermitian. Whether it's correct or not.
It's not correct.
Yeah, not correct. Because it will become BA, right? Sorry. I mean BA commutator it will become. So it's the thing that we just did. Pull dagger and we saw it is anti-Hermitian. It will become BA minus AB, so that is BA commutator. So this is not correct. Okay, now D is also not correct. Why? It says the product AB is Hermitian. So AB Hermitian meaning AB dagger should be equal to AB. And then the condition that it is giving is, okay, AB whole dagger is actually B dagger A dagger, which is BA if A and B are Hermitian, and for AB to be Hermitian, it should be equal to AB, and that is true only when AB commutator is 0. This is true only when, if and only if AB commutator is 0, but the condition it says is if and only if AB commutator not 0, so that is incorrect. Okay, now these first two statements, eigenvalues of Hermitian operator are purely real. Let's see, we can show this. So let's consider, let A be a Hermitian operator. And consider psi to be its eigenvector with eigenvalue A. Okay, so this is an eigenvalue equation, and we need to show that A is real if A dagger is, so A is Hermitian, which means A cap dagger is A cap. So if we take its expectation value, we get A. psi inner product. Now, so what is the basic definition of Hermitian conjugate of an operator? This I told earlier. So this is same as a cap dagger psi 1 psi 2. Now if A is Hermitian, then this is a cap psi 1 psi 2. Okay. So that is what it means for a Hermitian operator. Now what we can do is take conjugate of this expectation value of this equation, conjugate of both sides, psi a cap psi whole conjugate is equal to a star. So this would mean, okay, since A is Hermitian, so we can write it this way. Using hermiticity of A, and then this conjugate means, so alpha beta conjugate is nothing but beta alpha, so we get right. So we had this equation 1 and now we have this equation 2 after we took Hermitian conjugate of equation 1. So if we subtract these two equations, 1 minus 2 if we do, we get A minus A star psi inner product equal to 0. Since this is this is a vector, non-trivial eigenvector of A operator, so this inner product must not be 0, which implies A minus A star equal to 0 or A equal to A star. So the eigenvalues of any Hermitian operator are purely real. Okay. Now this second statement says the eigenvectors corresponding to different eigenvalues of a Hermitian operator are orthogonal. So let us see how to show that as well. So let us start with psi 1 eigenvector with eigenvalue, let's say a1. Psi 2 is another eigenvector with eigenvalue a2. Okay. Now these two equations we have. Now if we hit equation 1 from left by psi 2 and equation 2 from left by psi 1, we get psi 2 a psi 1 is equal to a1 psi 2 psi 1, and from 2 we get psi 2 is equal to a2 psi 2. Okay. Now let us take Hermitian conjugate of this equation 3. Conjugate of, let's say, 4. What do we get? Psi 1. This expectation value is a number, so we just need to take conjugate. So A star, psi 1, psi 2 star. But we saw that eigenvalues of Hermitian operators are real. So now we can replace it by just A2. Okay. Now since A is Hermitian, so this we can write as A cap psi 1, psi 2. Using hermiticity of A. Then when we take conjugate, alpha beta becomes beta alpha, so this is psi 2 A psi 1, likewise psi 2 A psi 1. Okay. So what do we have now? Equation 5. So now subtract 5 and 3. So left hand side is same. 5 minus 3 if we do. Right hand side we have A1 minus A2 psi 2 psi 1. Correct? That is equal to 0. Now we started with two different eigenvalues. So of course A1 is not equal to A2. That's what it says. Statement: eigenvectors corresponding to different eigenvalues. So A1 not equal to A2. Since A1 not equal to A2, so we get psi 2 psi 1 inner product is equal to 0. So that means eigenvectors corresponding to different eigenvalues of a Hermitian operator are orthogonal. Okay. Question 8. Consider an unnormalized state which is given in terms of three normalized vectors as follows, where phi n are eigenstates of an operator B such that this holds for n equal to 1, 2 and 3. Then the expectation value of B for the state psi would be, so your answer should come out to be an integer. So you do this and let me know what you are getting for the expectation value of B for the given states psi. So the statement is clear, right? What you have to do? You need to find out expectation value of B for state psi, meaning you need to calculate this quantity. Okay, and the question says that this phi n, these are all orthonormal vectors, meaning phi n phi m is equal to delta nm, which is equal to 1 for n equal to m, 0 for n not equal to m. Okay, so that is all is given here.
In 19. You know?
One moment. No, shouldn't be 19. It's 3. Answer is 3. So you should use this condition, that is b on phi n is n square plus 1 phi n for n equal to 1, 2 and 3. Anyone else? You can maybe do it again.
Ma'am, the answer comes out to be 3 if we use psi as it is, but it is given that it is unnormalized state, right? And for calculating expectation value, we should be using the normalized state, right? So we first have to normalize it and then calculate it.
Oh, I see. I didn't notice that.
It is given that it is unnormalized. If we take it as it is, then the answer is 3. But that would be wrong, right? Because we
Yeah,
first have to normalize it.
exactly. Then I just saw the answer given was 3, so that's what I told. I haven't solved it myself. Okay, let's do it then. So
Okay.
then the expectation value would be psi. So psi inner product, if you take, what are you getting? Half plus 1 by 5 plus 1 over 10, right? So what, 10, 8 by 4 by 5. Okay, yeah, then phi psi. Okay, let's do first b operating on psi vector. It's 1 over square root 2, then n square plus 1, that is 1 plus 1 phi 1, plus 1 over square root 5, n square plus 1 4 plus 1 phi 2, n square plus 1 9 plus 1 phi 3, square root 2 phi 1 plus square root 5 phi 2 plus square root 10 phi 3. So would then be 1 over square root 2 phi 1 Okay, we now have that state with us. Yeah, this itself gives 3. One plus 1 plus 1, 3. But if we, so the expectation value of B inner product 3 divided by 4 by 5. Is this what you are getting?
Yes, ma'am.
Okay, good. So here, I don't
Madam,
know why then this question says answer should be an integer. I don't know.
Madam, can you explain one thing that it is, please scroll down, madam.
Yeah.
Here we are doing the B cap into B cap on Kate side. Then we are getting this one. This one root 2 psi 1 plus root 5 psi 2 plus root 10 psi 3.
Yeah.
So when we are doing this, we are operating with brass psi.
Yeah.
So why should this one is 1 by root 2 and 1 by root 5 and 1 by root 10?
No, what we are doing is, so B psi kit, we got this, that we have replaced here, and this is nothing but the state psi, not B acting on psi.
Okay.
Yeah, because B has already acted on this kate vector psi, and this dual vector we are writing as it is.
Okay.
Yeah. Okay. Yeah, I don't know then why this question says answer should be an integer. Okay, I will check with the instructor maybe. Consider a pair of orthogonal kits V1 and V2. What is the dual of this kate V? Yeah, you can just tell me which one is the answer.
B1.
Yeah. Okay, now consider an operator phi 1 kate phi 2 bra, where phi 1 and phi 2 both are orthonormal. Then what the correct statement about B cap square and B dagger is which one?
C.
C?
Yes.
Okay. So B cap square is, yeah, it says orthonormal phi 2 and then again phi 1 phi 2. Now this is 0, so this is 0, and B cap dagger is phi 1 phi 2 dagger, so it's phi 2 phi 1. B dagger is phi 2 phi 1. Now this is 1, so it's phi 1 which is a projector. So yeah, C option is correct. B cap square is 0 and this is a projector. Projector corresponding to phi 1. Okay. Okay, so for this question, we were given a Hermitian operator, and then we had to say eigenvalues. We had to show that eigenvalues of Hermitian operator are purely real. Now suppose you are given a unitary operator, then what happens to the eigenvalues? Do you know eigenvalues of unitary operator? Are they real, imaginary, or what?
Can you repeat the question, madam?
I am saying that eigenvalues of unitary operators are what? Is it real, imaginary?
One.
Huh?
Should be one.
Okay, so eigenvalues of unitary operators are imaginary and they are of unit modulus. So what I mean by that, suppose U is a unitary operator, some eigenvector is giving you eigenvalue U times psi. So if I take its Hermitian conjugate, if I take its Hermitian conjugate, U cap dagger, okay. Suppose another vector, call it psi 1, so this when I psi 2 star U2, so what do we get? So U dagger U then maybe call it 2. So U dagger U is identity because it's unitary. Equal to 0. So it gives so if we could have done it for arbitrary way. So any eigenvector, let's call it I, and call it J. Okay. If ui is if I is equal to j, then we can see, right, this is inner product of two eigenvectors, and that has to be non-zero, not equal to 0, and what we get is 1 minus ui star ui equal to 0, or ui mod square equal to identity. Okay. And then these two should be 0. So the eigenvectors corresponding to different eigenvalues of unitary operator are also orthogonal. If so, why that should be the case? Because if I is not equal to j, then ui star uj is not equal to 1, because here we have already proven that ui mod square equal to 1. So when I is not equal to j, ui is not equal to uj, so that means ui uj star is not equal to 1. So that means this is non-zero when I is not equal to j, and this eigenvectors corresponding to two different eigenvalues has to be 0. Of a unitary operator are orthogonal. Okay. Okay. Okay, having said that, now in the last assignment we had two more problems which we didn't solve.
Madam, it is of unit modulus and is imaginary. That means is it j or minus j?
So sorry, what was the question?
You told that the eigenvalues of a unitary operator,
Yeah.
having the imaginary value
Yeah.
and unit and the unit modulus, means mod value is 1.
Yeah.
That means the value is j or minus j.
No, it can be any complex number a plus ib such that the mod value, that is a square plus b square equal to identity.
Okay.
Right? So a can be 1 over square root 2, b can be 1 over square root 2. Then 1 by half plus 1 by half will still give you 1.
Okay.
So mod square of the eigenvalue should be unitary. Mod square of the eigenvalue should be 1. So that means the eigenvalues are indeed imaginary. Okay, so let me open the last assignment. So this assignment we were solving, this question we were solving last time, but we didn't have time, so we can maybe do it now. So the question was, we had a free particle with this initial wave function. We had to normalize it, so that normalization we did. Normalization constant turns out to be 2a over pi to the power 1 over 4. Now B part says find what is psi x comma t. So for a free particle, for a free particle, the solution looks something like this. Psi x comma t is integration over dk phi k exponential I kx minus et, but e is h cross square k square over twice m t. Okay, where phi k is inverse Fourier transform. I think square is square root 2 pi or something. Let me check. Yeah, square root 2 pi minus infinity to infinity, and phi of k is inverse Fourier transform of psi of x at d equal to 0 dx. Okay, so once we have phi, so psi x comma 0 is given to us, so using that we can calculate what is this phi k, and then that we can substitute here to determine what is psi x comma t. That is all. And also for free particle you need to know what is the general solution, so this you need to know in order to proceed. So let's evaluate what is phi k. 1 over square root 2 pi infinity. What is psi x comma 0? It is this. Now a we have already computed, so okay, let me write a for the time being because it's a big number. Exponential minus a x square dx exponential minus a x square minus I kx dx. But this kind of integration you know how to perform. You have to make it so x square appears and x also appears, so you can make it square, like what I mean is minus, oh god, yeah, what I mean is minus ax square minus ikx take minus common, so ax square plus so this is same as x plus pi to a into b, where b is ik over a plus ik over a whole square minus ik over a whole square. Okay, but this is independent of x, so we can take it out. Exponential.
Ma'am, there is x square.
Oh, right, yeah, thank you. So it becomes minus a x plus I k over a whole square. I square will give you plus, so k square over a square dx, a over square root 2 pi exponential minus k square over a, sorry, there should be a 2, sorry, this 2 should also be there because that 2 we have just added to make it a 2ab term, plus ik over 2a, here also there will be 2a, okay, so minus k square over 4a, then integration minus infinity to infinity exponential minus a x plus ik over 2a whole square dx, but this is nothing but Gaussian, so what do you get? Exponential minus k square over 4a square root pi over a. Okay, so you can change the integration variable, so x, instead of calling it dx, you can call it d of x plus ik over 2a, because ik over 2a is anyway constant, it gives you dx only, and Gaussian integration is minus infinity to infinity exponential a x square dx, that is square root pi over a. That formula we just used. Okay, so square root 2, so pi gets cancelled out, and okay, let me write it. A was, what was a? A was a normalization constant. Okay, then this term also remains. Okay, so this pi gets cancelled, and this, if we simplify, 1 over 2 pi a to the power 1 over 4 exponential minus k square over 4a. Okay, so that is our, that is what? That is phi of k. So this phi of k we have obtained. Now we go back to psi xt. Psi xt is 1 over square root 2 pi infinity to infinity exponential, sorry, phi of k exponential I kx minus et, e is h cross square k square over pi sim for a free particle dk. Okay, now phi of k we now have with us, so we substitute it here, 1 over 2 pi a power 1/4 integration minus infinity to infinity exponential minus k square over 4a times this entire thing. Okay, now this is having similar kind of expression that we had for phi k, because it involves k square and k. Now the integration is over dk, so and initially for phi k it was over dx, that was the inverse Fourier transform of psi x comma 0. So now again we have to do the similar thing, 1 over square root 2 pi 1/4 exponential, what do we get? We need minus some a times x square, sorry, here it's k square minus some a constant times k square. Okay, so we now know what is the relation. So when we have exponential minus ax square ikx, then the final result that we get is exponential minus k square over 4a square root pi over a. So this we will use now instead of doing this steps here. We'll just use this expression, I mean this result. So let's write it. 1 over 4a plus I h cross square t over 2m. So this is our a, that constant. This entire thing is like that constant a, plus ikx dk. So this gives 2 pi to the power 1 over 4. Those are the constants we already have. Exponential minus k square over 4a. But what is a for us now? It's this thing. Okay. Times square root pi divided by a. Okay, that is the result for psi x comma t. Okay, now this can be rewritten. I haven't made any mistake. Okay, sorry. Initially it was integration was over dx, that's why it was minus k square over 4a, but now integration is over dk, so the result that we get is minus x square over 4a. So this can be rewritten as 2a over pi to the power 1 over 4 1 over square root of 1 plus 2I h cross sorry, there was one mistake here. So when I say energy is h cross square k square over twice m, it's fine, but what is the factor that we get for the time dependence? It's exponential minus et over h cross. So energy is this factor, but there is 1 over h cross factor, 1 by h cross factor. So that will make it h cross only, not h cross square. So this is not h cross square but h cross. So this square I am taking out. Okay. Then it makes sense. 2I h cross at divided by m exponential minus ax square divided by 1 plus 2I h cross t a over m. Okay, that is psi x comma t. Okay. Okay. Now the third part is find mod psi square and express the answer in terms of this quantity omega. So what is mod psi square? Mod psi square is psi star psi. What do we get? So this is just a constant, so it will become 2a over pi to the power 1/2. When we take star, this will change its sign, 1 over square root 1 plus 2I h cross at over m, 1 minus 2I h cross and this terms will also change sign. So what we get is that exponential minus a x square times okay. So if you simplify this, so these two are in the exponent, so they get added up, and if you simplify it, you will get 2a over pi to the 1/2 exponential minus 2a x square divided by 1 plus, so these two will get multiplied, so it's 1 minus x square, and because of I it will become plus 1 plus 1 plus 2h cross at over m whole square divided by 1 plus 2h cross at over m whole square, and in terms of that omega, so omega was a divided by 1 plus 2h cross at over m whole square. So in terms of omega, psi of xt mod square is, so this square root a we take with this term, so it becomes omega exponential minus, you can say it's 2 omega square x square. Okay, now the third part is also asking us to plot psi of x t mod square as a function of x at t equal to 0 and t2 which is greater than t1 greater than 0. So for different times we need to plot that mod psi square. So okay, so this is, so as a function of x, so call it some different function of x comma t. So we need to plot this function f versus x for different times. So as you can see, it's a Gaussian. We need to see how this Gaussian will change as time changes. So what I mean is, so Gaussian looks something like this. So let's see how the width at half the maxima changes. So what is the maxima? So at x equal to 0, what is the value of this function? It's square root 2 pi times omega. So that is the width, that is the height at x equal to 0, omega. But now you see omega also depends on time. So as time changes, omega will change. So as time increases, so denominator increases, so omega basically decreases. So we can see that this should be something like this, right? So let's say for t equal to 0,
Madam, what is the height root over 2 by pi omega?
Full, okay. Yeah, I mean, sorry, this I was not considering because that is a constant. Yeah, square root 2 by pi omega. Yeah, that is the, so at t equal to 0, let's plot it for t equal to 0. So at t equal to 0, omega is nothing but square root a, correct? So the function f x comma t, that is 0, is square root 2a over pi exponential minus 2a x square. So at t equal to 0, it's something like this. Square root 2a over pi is the height, and then it's the Gaussian is exponential minus 2a x square. So now the question actually says to plot this particular curve for different time values with respect to x. So when time increases, now I was saying that time increases, then omega decreases. So as time progresses, your Gaussian will be like this. So this is sorry, for t1, but t1 is greater than t2, and again it's for t2. So, and this is for t equal to 0. So where t2 is greater than t1, greater than 0. Okay, that is it. Okay, so second part is also done. Now we need to find out what is this expectation values of x, p, x square and p square. So let me do expectation value of x and other things you can figure out. Well,
Madam, what is the omega here? It is the any angular frequency.
No. Omega is just a quantity which is defined like this, which is
Means as the time increases, it is following the x-axis more.
no. As time increases, omega is decreasing. So omega is defined like this. I mean, question says you express
parallel to x-axis.
Huh? Sorry, say that again.
I'm telling that as the time increases, the omega is getting flatter and flatter. Means
No, omega is not getting flatter. Omega is the height of this curve. So this is omega at t1. So value of omega is at x equal to 0. Sorry, this is not omega, but this is omega. This is square root 2 by pi omega at t1. This point, this height. Likewise, and this flatter, it's the curve is becoming flatter because exponential is also having that omega in its exponent. So if you calculate the full width at half maxima, okay, so let me do that. So how can you calculate full width at half maxima? So let's say at x star some time t, so what do we mean by full width at half maxima? So this is, suppose this is half the maxima. So if your maximum value is square root 2a over pi, then this value is half of that maxima. I mean, at this point the height is half of that maximum value. So that's what this and this, as you will see, when time increases, this full width at half maxima actually increases and width decreases because omega itself decreases. So okay, so let's say at x star, so at x equal to x star, the width is half the maximum. any t, let me do it. Square root 2 by pi omega exponential minus 2 omega square x star square is half omega, sorry, by maxima. When is it maxima? At x equal to 0 it's maxima, so it's half omega. So at x equal to 0 the value of the function is maximum, so that's what we mean. We need to figure out what is x star when the value of that function will be half of its maximum. So omega gets cancelled out. Sorry, function will also have this square root 2 pi factor, square root 2 by pi. So what do we get for x star? So it's 2 omega square x star square is ln2, or x star square is ln2 divided by 2 omega, or x star is plus minus 1 over omega square root ln2 over 2. So full width at half the maxima is nothing but 2x star. What is this x star value? X star is nothing but the position. This is x star and this is x star in the negative, minus x star, I mean this is minus x star and this is x star. So full width at half maxima is 2 times x star, that is 1 over omega square root 2 ln2. Okay, so now what I was saying is, as time increases, omega decreases, full width at half maxima increases. So that's why this is becoming flat. At half the maxima, this is increasing. The full width at half maxima is increasing. That's why the curve is becoming flat, as well as since omega is decreasing with increasing time, the height of the curve is also decreasing. You understand?
Yes, madam.
As t increases, omega decreases, so the maximum value of the Gaussian decreases, and full width, and for increasing time, full width at half the maximum increases. Okay, so the curve becomes flatter. With increasing time. Okay, now this expectation value of x, oh, that is easy because the answer will turn out to be 0. Let me just say that, and the other things I will leave it for you. So expectation value of x is minus infinity to infinity psi x comma t star x psi x comma t dx. So what is psi x comma t? It's here, this thing, it's 2 over pi omega square, but omega square is independent of x, so then this is constant. Then x exponential minus 2 omega square x square, but from yeah, so omega is real, so no where it's complex. So what we get is 4 omega square x square, right, equals 2 omega square x square 4 omega square x square dx. Now you can see this is odd integration. When you do evaluate odd integration from minus infinity to infinity, it becomes 0, so it's 0. Now from Ehrenfest theorem you know that momentum, expectation value of momentum is ddt of expectation value of x, so that is also 0. So both x expectation value and p expectation values are 0, but these two will not be 0, so you go back and do that integration. So x square expectation value would be infinity to infinity x square psi star xt psi xt dx. Likewise p square will be the same, but now p you have to write in terms of minus I h cross d ddx, and then compute it. And what is this sigma x? Sigma x is square root of x square expectation value minus x expectation value square. So since this is 0, so this will be just x square expectation value square root. Likewise expectation value of p is also 0, so the uncertainty in p will be square root p square expectation value. So once you know these two, you also know these two. And fifth question says, does the uncertainty principle hold? So you need to see whether sigma x sigma p is of the order of h cross by 2 or not. Okay, so let me give you the answer. X square expectation value will turn out to be 1 over 4 omega square, and p square expectation value will turn out to be h cross square a. Okay, so then you can see, you will be able to argue whether this uncertainty principle holds or not. Sigma x sigma p, whether it is greater than or equal to h cross by 2, you will be able to argue from these two values, because you know what is omega. So see, omega is this thing. At t equal to 0, what is omega? Omega is just square root a. So your sigma x at t equal to 0, your sigma x is square root this quantity, which is 1 over 2 omega at t equal to 0. Sorry, at t equal to 0. So sigma x is square root x square expectation value. Now x square expectation value is this, that is 1 over 2 omega, and at t equal to 0, omega is 1 over 2 square root a. Sorry, sigma x is 1 over 2 square root a. So this square root a from this will get cancelled out this square root a, and you will get h cross over 2 exactly. So the uncertainty principle holds. So I just told you, but you can do it explicitly and then check. Okay, are there any questions? Okay, if no questions, we can stop here. We will make next week. Thank you for joining. Okay, I have there are no questions, so let us stop here.
No, can you write the final answers, solutions for us?
Oh, I did that.
That is the.
Yeah, you got disconnected that time. So the final answer for x square is 1 over 4 omega square. For p square expectation value, it will be h cross a. Okay, and so sigma x is sigma x is defined as x square expectation value minus x expectation value square. Since this is 0, so it's just square root x square expectation value. So you have this with you, so that is your sigma x, and square root of this quantity is your sigma p. And I was saying that for E part, it is asking whether uncertainty principle hold or not. So you need to show that product of these two is greater than equal to h cross over 2. Since sigma x involves this omega, and you know how omega changes with time, you can say whether this is greater than equal to 0, greater than equal to h cross by 2 or not. So at t equal to 0, what happens? Sigma x is nothing but 1 over 2 omega, because square root of this will be 1 over 2 omega. At t equal to 0, you can see that omega is square root a. Omega is square root a at t equal to 0. So that is sigma x is 1 over 2 square root a. Okay, and sigma p is square root h cross a. Why is here square root? Is it h cross square? Oh, sorry, I wrote it wrong. It is h cross square a. So sigma p is h cross square root a. So you can see at t equal to 0, the uncertainty principle holds exactly, meaning sigma x sigma p is h cross over 2, and as time increases it will be greater than equal to h cross over 2, because omega appears in the denominator, and you know as time increases omega decreases. So this sigma x sigma p will be greater than or equal to h cross by 2. Clear?
Yes, ma'am. What is the value of x and p? The expectation value of x and p?
Oh, that we derived. So expectation value of x will be 0, because this is odd integration. This entire thing is even under x going to minus x, but this is odd. X is odd under x going to minus x. So this expectation value of x is 0. And using Ehrenfest theorem, you can say that expectation value of p is also 0, because expectation value of p is dx, expectation value over dt. Clear? I mean, if you are not convinced, you can go back and do this integration, it will be 0. Okay. Any other questions? Okay, then let us stop then. Okay, bye.